Okay, welcome back. We are now going to be discussing the general equilibrium and the steady states of the neoclassical growth model. So let's start with the general equilibrium. This is section 4.4. So the general equilibrium is a set of equations describing the behavior of the whole economy. So what are these equations going to be? Well, 1, Euler. 2, the resource constraint. 3 is investment. Law of motion of capital. 4 is going to be production. Right, so with these 4 equations written out, I will be able to describe the aggregate economy. So, without further ado, let's get started. What's the first one? Euler. We have our Euler equation for the first one. 2. Resource constraint. Y equals C plus I. 3. Investment. Law of motion of capital. And then 4. Y equals A times K to the alpha. With these 4 equations right here, I can describe the whole economy. Why? Well, if there is a change to something, if there's a change to an endogenous variable in here, it's going to feed through the system and it's going to affect all of these equations in some way, shape, or form. Right, let's say change KT plus 1. Well, KT plus 1 changes, that changes investment, so that changes consumption, changes the marginal product of capital, which will change everything within the Euler equation. And if this gets updated one period, it changes everything in production. Right, beta changes, right? Beta is an exogenous variable, it's a parameter. Beta changes. It's going to change a bunch of stuff in all of these. But let's say I just left out, I don't know, the law of motion of capital. Well, we'd have some weird changes going on that would not make sense for what we would expect to see in the economy, from what even we've seen given changes looking at real world data. This stuff just it wouldn't line up, it wouldn't make sense. So, by having all 4 of these equations, we can describe in full the behavior of the economy. It is, quote unquote, closed out, so to speak. So we've closed out the economy, meaning that there is nothing that isn't being described adequately in one of these equations. Right? We can say this system is identified. And there we go. But wait a minute, is it identified? What about A? Do we want to talk about A, or do we want to just ignore A for a minute? Let's talk about A. Because if we're actually considering the existence of shocks, I can't say the system's identified. I would need one more. We need a process for AT. Let's see what I want to use gamma. I use that to describe the process that A follows over time. So this says AT plus 1 is equal to gamma, some estimated slope coefficient, times AT plus error. Right, this right here, what's going on here, allows, because let's say if I wanted to look at AT instead. So AT plus 1 equals gamma times AT plus epsilon T minus, or T plus 1, my mistake. Well, if I wanted to look at what AT is today, that source of shocks, it follows this process here. Gamma times AT minus 1 plus error that would enter into the equation today. So this actually makes it identified. Now I can use this one or I can use this one. It doesn't particularly matter. I'm going to use this one, AT and AT minus 1. But if I were to update it one period, I just update it one period. So I get that. And that allows for technology shocks. Because remember, just like in the solo model, AT is a source of technology shocks. This allows for technology shocks to enter into the equation, or set of equations, and it describes some process that this shock follows over time. Now, this system is identified. Aren't we happy? So the system's identified with these equations here. And that will wrap up this section for the general equilibrium. It's a relatively short section because it's just list the equations. That's it.